Hello, this is Mrs. Davis. I'm teaching AP Calculus Lesson 7.2, Verifying Solutions of Differential Equations. So we still haven't learned how to solve differential equations, but we have learned how to write them, and now we're going to learn how to verify that something is a solution. And so let's try to remember a few facts that the general solution that you get, that's the one that's got the plus C, of a first-order differential equation represents a family of curves, and the family is because C can be anything, which we investigate. So we're going to be talking about C a lot. To see how there's a whole class of functions you can satisfy this particular differential equation that can satisfy a particular diffeq, consider the family function of y equals e to the bx. So this is going to be us showing, they want us to show that y equals 2e to the x and this one, y equals e to the negative 4x, are both valid solutions for the differential equation y prime prime plus 3y prime equals 4y. So all you have to do is you need a y, you're going to substitute stuff into this one because you're going to use these. So you're going to get y prime prime. First of all, you got to do it two of them. So this is going to be proving y equals 2e to the x is a solution, and then y equals e to the negative 4x is a solution. So you're going to be doing this twice to show both of them are a solution. So you would take the derivative of y equals 2e to the x to put in there. So y prime is equal to 2e to the x, and y prime prime is equal to 2e to the x. So if I'm substituting everything back in, I guess I should have made my arrows better. So this one is going to the second derivative, and this one is going to the first derivative. And we just have to make sure that this statement is true when we put all that in. So y prime prime was 2e to the x plus 3 times y prime, that was 2e to the x, and that's equal 4y. So now you can say, okay, for y, okay, I should have substituted in y, sorry, is equal to 4, and then y, right? I'll put y, and then that's equal to 2e to the x. So that's equal to 4 times 2e to the x. So this is 2e to the x plus 6e to the x equals 8e to the x. And that's true. We have 8e to the x equals 8e to the x. So that one was a valid solution. So y equals 2e to the x is a valid solution to the differential equation y prime prime plus 3y equals 4y. So let's go over here and look at e to the negative 4x. So we would take the derivative y prime is equal to, just take the derivative, negative 4e to the negative 4x. Y prime prime would be 16e to the negative 4x. All right, and so then we go back to our differential equation and we put these values in. So we get 16e to the negative 4x plus 3 times y prime, which is negative 4e to the negative 4x, is equal to 4 times y, which is e to the negative 4x. All right, so let's do the math out here. We have 16e to the negative 4x, and then we have, 3 times that, so that would be minus now, because I have a minus 4. So minus 12e to the negative 4x equals 4e to the negative 4x. And 16, if you factor out e to the negative 4x, you get 16 minus 12 equals e to the negative 4x, 4. So you get 4 equals 4. So that means that y equals e to the negative 4x is also a valid solution. All right, so we're going to just practice a few of these. We have, is this a solution to this differential equation? So we need the first derivative right here, and then that's all we need. So if we say dy dx, because they use dy dx, is equal to negative, we have let's see, if you multiply 1/2, or you're putting negative 0.5 in times 3e, so that would be negative 1.5 e to the negative 0.5x. And so then you can now put it into the differential equation. So negative 1.5 e to the negative 0.5x equals 0.5 times 15 minus y. And so y is 3e to the negative 0.5x. All right, so let's simplify this. Let's see if we have, plus 15. I forgot, right? Sorry, hang on. Got to go back here. And then we have 15 minus this, right? Plus 15. That's the whole y. And so this is 15 minus 3e to the negative 0.5x. And then you'd have 15 minus, and then this would be 15. So the 15s would go away, and you'd have 0.5 times 3e to the 0.5x, which is the same thing, negative 1.5 e to the negative 0.5x. So yes. And let's look at this one. G of x is, here's the equation they want to know, is that a solution to this differential equation? So we're going to need g prime of x. So g prime of x is easier than the other one, 4x cubed minus 5. So then we're going to put it into this, is 4x cubed minus 5 equal to 5x plus 4, and this, in this case, y is x to the 4th. This is like y, right? X to the 4th, so minus 4, x to the 4th minus 5x over x, which is just x. So we have 4x cubed minus 5 is 5x plus 4x to the 4th minus 20x over x. So 4x cubed minus 5 equals, let's see, 4x to the 4th minus 15x over x, or 4x cubed minus 15, and they are not the same. So no g of x equals x to the 4th minus 5x is not a solution to g prime of x equals 5x plus 4y over x. Okay, and lastly on this page, find a general solution. Okay, so in this case, they just want us to have the c. And so this is our first time kind of solving, find a general solution for this differential equation. And what you learn to do is, if you take the derivative of dy dx, you get y, right? So this is, so what we can do is, if we take the derivative of both sides, the integral of dy dx is y. And if we take the integral of both sides, we end up with y equals, which is what we want, the integral of dy dx is just y, and a general solution should be in the form y equals. All right, so let me teach you one thing. You usually get a point for, and we'll get to this, but separation of variables. So make sure when you're getting ready to do this, dy dx is 3x squared. So then you're going to do a separate line where you take the integral of each side. So that's the integral of 3x squared dx. Okay, and now that's y equals, and this would be 3x cubed over 3, so that's x cubed plus c. And that's a general solution. So that's it. We solved this for a general solution, this differential equation for a general solution. That was already in terms of dy dx, so we just ended up taking the integral of both sides. Okay, that's the end of this video.